Welcome to Coding Adventures. Today we are continuing the lesson about run-length encoding algorithm, and we're gonna attempt today to implement a compressor and decompressor for a binary file. I'm thinking about an image and then display it on the canvas. All right, so let's get started. Welcome back. So yesterday we discussed about the run-length encoding algorithm, and we saw that is a very simple algorithm that can be used to encode various pieces of information, and yesterday we encoded text. Today we're gonna try to encode and decode binary information. And for this I prepared something. I prepared a binary file, and I actually, it doesn't look quite like binary, it looks like a bunch of numbers. Just to avoid opening binary files in JavaScript, at least for now, we're gonna just take all this information, which is a series of bytes, and we're gonna put in a JavaScript file, and we'll consider that we open the binary file, and this is the content of the file, and now we're gonna try to decompress it. All right, so let's do this one first. I'm gonna copy all this content in the file, place it on the clipboard, go in the code editor here, and eventually let's have it, maybe have a function, get image. We know already that this one is an image, and this one maybe should return an array of bytes, this function, which is exactly the array of bytes that we prepared ahead of time. All right, so let's run this one, make sure we don't have any error, and we don't have any error indeed. I'm gonna name this one binary run-length encoding, save it, and place the program on the chat. All right, let's place the program on the chat. Of course, if you try to run it on your side, you should not get anything. Now, the task is to basically decompress all these bytes, and then hopefully we'll get an image back, exactly like we put the name of the function, and then display it on the screen. But before we actually start decompressing these bytes, we need to understand how these bytes were created. And for this, I'm gonna take my notebook. So let me explain you the algorithm that was used to compress these bytes. And with this knowledge, we're gonna try to implement a decompressor based on that algorithm. All right, I'm here on my notebook. And let me place some bytes here, some random bytes. Let's say 23, 47, 15, 15, 15, 15, 0, 2, maybe 9, 0, 0, 1. All right. And the story goes, once upon a time, this was basically a file. It was living in a binary file, uncompressed, and it was consisted in a series of bytes, many bytes, in fact, not only these ones. And then we implemented a compressor and we turned this file into a compressed file. So what can we notice here? Since we are talking about run-length encoding algorithm, we know that basically we need to detect sequences that are repeating, such as this one perhaps here, and I think there's another sequence over here, and somehow encode these sequences in a way that will take less space in the output file. So the convention that was used in the particular case of this file, so that to end it up with these bytes, is the following. All the bytes in the original file were just transferred in the compressed file. But each time when a sequence of several identical bytes was discovered, like in this case we have 4 bytes with value 15, this was encoded in the following way. A 0 was encoded, and then the byte, the actual byte 15, and then how many times is repeating. All right, so the sequence here of 4 bytes transformed in a sequence of 3 bytes. It's not a very big saving in this particular case, so it's 4 bytes initially, and then was converted into 3 bytes. But imagine here, instead of 4 bytes, we would have 100 bytes, right? So that would be quite a saving. Instead of about 100 bytes, we'd have compressed them in 3 bytes, which was kind of big, right? All right, so let's continue. Now, here it's a 0. And since we cannot use the algorithm that we used yesterday with the encoding of the 7-bit ASCII characters, and we cannot reserve 1 bit to mark that that particular sequence is it's compressed. In this particular case, we use the full byte, like byte 0, to indicate that the following 2 bytes represent have a special meaning. Basically, represent what byte is repeated and how many types. So basically, this is a byte that is repeated. This is the counter, and this is a special marker. Right? So in this way, when we're gonna read back the compressed file, which is the one on the bottom here, we're gonna read it this way, and each time we're gonna encounter a 0, we'll know that we need to take the following 3. But here in the original file, we have a side effect of using 0 for a sequence like that. Since we have a 0 here, we cannot just transfer it like that and then continue with putting here 2 and 9, because if we do this, if we put here a 2 and a 9, the one from above, when we're gonna read back, we'll interpret that number 2 will have to be repeated 9 times, which is not the case. Therefore, each time a 0 it's encountered, actually will be encoded as this. 0, we're gonna put what byte is repeating, which is byte 0, and 1 time. So this is very not an intended use of the compression, because we transform byte 0 that appeared once, here originally was 1 byte, we transform it in 3 bytes. Basically in a marker that say that byte 0 repeats 1 time, which was 1 time only anyway. And then we have 2, we'll put it here, we have 9, and then we have here 0, 0. Here this will be encoded as, again, with a 0, and byte 0 is repeating 2 times. So this is encoded like 2 to 3, also a disadvantage situation, and now it's encoded here 1 to 1, so here will be encoded as 1. All right, so based on what we can see here, I think this was kind of a very disadvantage situation to use compression, because the original file that was I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bytes was encoded in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 bytes. So this is actually quite expected. RLE algorithms, or run-length encoding algorithms, sometimes they produce output that is bigger than the input. And yesterday we didn't see this particular situation because we used that special bit, but today we are seeing this situation. But this is an exception. In majority of information that we are encoding, we usually have bigger sequences like this one that they repeated. So this will make up for the very few situations when 0 appears alone. Yeah, this is actually the disadvantageous one, or appears at least 2 times. Because here if we have 0 repeating 100 times, that is fine. It will be encoded in 3 bytes. Here, if the sequence is 200 bytes the same, it will be encoded in 3 bytes. The only situation that is problematic is when we have a 0, and because this one will be encoded in 3 bytes, and this is because we use 0 as a marker in all these sequences to indicate that it's a compressed sequence. All right, so now we know how was the original state of the file. It was a file in this state and was compressed like this one. So if we are looking here on the in the code, we can even see here, we can spot some zeros. So we assume, okay, we have a 0. That means that byte 253 needs to be repeated 3 times, and then we have a 0, means that byte 243 needs to be repeated 3 times. And then this one, let's see if we can spot a sequence that repeats multiple times. I don't know, maybe here 0, byte 2 needs to repeat it 4 times, and so on and so forth. So the algorithm basically is pretty simple, and it's actually the same as the one that we used yesterday. We have to scan. Let's implement first the decompress. So decompress will take as input a compressed, an array. Let's say we'll take an input, an array of compressed bytes. There's no such thing as compressed bytes, but anyway, we're gonna say compressed bytes, and we'll output basically an array of bytes or uncompressed bytes. So decompress goes in this direction and compress goes in the other way. So this is decompress, and compress goes this way, right? We start from the original file and we'll try to compress it. But since we already have a file that was prepared ahead of time, like this one, we are really curious to see what is inside this file. So the algorithm is pretty simple. We have to scan it and copy in a uncompressed array buffer all the bytes that we encounter here. But each time we encounter a number 0, the marker 0, we look ahead at the next one, meaning that, okay, the next one needs to be repeated this number of times. So we look ahead 2 bytes, right? And that sequence basically of 3 bytes that we read, we're gonna expand it in however number of bytes that is basically this counter will indicate. All right, so let's attempt to write this this algorithm, and hopefully we'll be able to implement it. So again, we're gonna scan through all the bytes here. We're gonna check if the byte is 0. If the byte is 0, basically we're gonna read the next byte, which is basically the actual byte that is repeated. Then we're gonna read the counter, and then based on the counter, we're gonna push in the or in a buffer as many bytes of this value as the counter is. And if not, we're gonna just push 1 byte. Like when you read 1 byte, we're gonna push that one. All right, so I'm switching back here in the code. And let me attempt to implement the decompress function here for this binary structure. First of all, let's get in a variable. Let data equal get image. And let's see how big is this binary file. Println data.length. And since these are bytes, we could have used the new structure from JavaScript, which holds only bytes, which is more optimized, but we're gonna use just a plain old school array. All right, so this structure is about 100K in size. And we're gonna check also after decompression how big the data is. So let's implement that function decompress. That will take as an argument as some sort of a byte structure, and let's loop through this one. Let I equal 0, I less than bytes dot length, I plus plus. Let's say the current byte is bytes of I. All right, and now we have to check if the current byte is 0. This is the special situation when we encounter a byte that is 0. Let's increment I, and let's read the next one will be byte, right? So we are reading the actual byte. Yeah, we are overwriting this one. Let's overwrite that one because we don't need it. It will be bytes of I again. So if this was just a marker, what we read, well, the actual byte that is repeating is the next one. So we incremented I because we want anyway to move the pointer to the next one, and we read this. And we have also to read the counter. So let's increment I one more time, and counter, we have to define the variable. It will be again bytes of I. The same because we are incrementing here. And instead of saying here bytes plus 1, I want also to increment the I here. And in this way we skip this sequence entirely. So after this if, the sequence will be skipped entirely, and the I will point to the next value that we need to process. So let's define that count as well. Count, let's see what value should we give. So we read a byte, right? if byte is 0, it goes in here and we read which is the counter. But if it's not 0, it means that the count is 1. So let's say we read a byte here in the middle, 19. 19 is repeating just once, right? So the count is 1. Let's initialize here count with 1, and if the byte is 0, we'll overwrite actually the count with the value that we read on the third position there. So looks kind of okay. So we are looping, we are reading byte and we identify byte and count. We need to push in some sort of buffer. Let's define a buffer here, AR, pretty generic one, an empty array. We are still inside the for, but after the if. So we read a byte and we read the count. So we need to repeat or to push into the output buffer as many values of this value as count indicates, right? So let's ignore for a second the if. Let's say that we just read a byte. It's just that. We read the byte and it's 1. Like, okay, we need to push it into that output sequence. But then we do also the check for the 0 and we actually correct if it's the actual value of byte and count. So let's do a small for here. We need to push multiple bytes. That's why you create a for. For j equals 0, j less than count, j plus plus. And what we're gonna do, we're gonna say ar.push, and we'll push inside basically byte here, right? Because we are decompressing the byte. Let's check carefully. Yep, looks correct to me. Let's return AR. All right, so this is our decompress function. And let's put a function here, decompress an array of bytes, compressed using RLE algorithm. And then let's say here, it appears such as byte, byte, or 0, byte, repeat. This is the sequence that can appear inside. Put here 0 used to indicate how many times a byte should be repeated. All right, and then we can have other bytes, and then we have here again other sequence. Of course, this one can be byte 1, byte 2, this is byte 3, this is 4, totally different byte here, and repeat it maybe different times. All right, let's call this function. Let's check it carefully again. We are iterating through all the bytes. Yeah, looks correct. Let's call this one. Let's decompress it. Image. Let's say image equal decompress. Hopefully we'll get back an image. That's why I'm calling the image the variable. Decompress of data, and let's print it. Print the length. Image, save it just in case, and run it. And I think we are correct, and I'm gonna tell you why in a second. But before then, I think we need to put some protections like that we put yesterday here. Remember yesterday we said, well, what about the initial sequence, for instance, like this one that we have here? What about somebody gives us a file and it finishes with a 0, just like that? Well, when we're gonna do the interpretation, we're gonna read this in order, and then we're gonna read the 0, and because this is a marker, we expect to read one more byte and then one more byte, but the file ends. So let's put a protection here. Before actually we advance, we can check if I is less than and then is bytes dot length. I think dot length -1. I may be off by 1. A typical programming error, but I think I'm correct. So if we can still read, we'll read the next byte, which should be the repetition byte. And then what if somebody gives us a file having a 0 and a byte, but doesn't include the repetition counter? Well, in that case, also we have to protect this area, because we cannot increment I past the length of the array. So let's say here, I think it's the same condition, bytes.length -1 is the same one, because by this time we incremented already I, right? So and we're gonna do all this, which should be correct, right? So but what about if we cannot go into these ifs? We read the byte as being 0 and we say to repeat it once, which is kind of correct, right? So if somebody gives us a file, just end it with 0 here. What, we're gonna put a 0? No, this is a marker. Maybe if byte is 0, immediately you know, assume the count is 0. So we reset the count. We don't do anything until we cannot go in these blocks, actually in the second block, when the count will be set. So I still am, yeah, I think these protections are good. Not necessary in case of our structure, because we just decompress it and work, but yeah, I'm getting the same result. So a small accomplishment, but let me explain you why I believe this is good. Let me grab my notebook really quickly. So let's actually go back here and put some more information. So this was let's say compressed data, and this is uncompressed data. All right, so I'm gonna write down what is the size, 480768. All right, I'm switching here back to the notebook. And why I believe the decompression worked is because of the following. What is compressed in that structure, it's an image of 800 pixels by 600 pixels. You know, typical image made out of pixels. And each pixel is encoded in 1 byte. So it's one byte per pixel, or 1 pixel per byte? 1 byte per pixel, to say like that. 1 byte per pixel. So let's see how many pixels are in the image. Pixels, 800 times 600 equal 480,000, right? Which is here exactly. But this is with an extra 768. So if we add this one, that will be 480,768. So which is correct. So let's see where these basically are coming. So the image already is encoded, like I mentioned, with 1 bit per pixel. And this is important right now. If we are moving into phase 2 of our implementation here, we decompress it, but we want actually to visualize it. And in order to visualize it, we need to understand the format of the image, right? Exactly like any graphical program. If it can visualize JPEGs, needs to understand how to handle JPEGs. If it visualizes PNGs, needs to understand how to visualize PNGs, or to play an MP4 and so on and so forth. So we need to understand the format right now to display it. Otherwise, we end it up just with a series of bytes. But so that's why I'm describing here how the format is compressed, or not compressed. We're beyond compression. At this point, there is no compression. We just have a structure, which is a binary file of this size, and inside it's an image. And I'm telling you the specs of this format and the image. So it's an image of 800 by 600 pixels. That's one thing. And it's another aspect, it's 1 byte per pixel encoded. And we have this 768. So why these extra bytes here? Well, so let's think of an image, like a regular image. Switching back here on the desktop, let's think about this old paper that I have here. And we see here blue, and we see here red for this bird, and gray and white and so on. Lots of colors. So if this is a colored image, how can we encode, for instance, let me put a few. So let's say these are the pixels, right? So let's say this pixel is black, and then you know, we have various colored pixels. This pixel is red, and then this pixel, it's let me bring a blue, and then, and you got the idea. We have different colors pixels, right? So and orange, and one more color that I have at my disposal here, and magenta, and even green. How many colors actually? That's a good question. How many colors can I have here on my pictures? Well, since we are encoding in 1 byte per pixel, actually, in 1 byte we can encode, basically, we know that in 1 byte we can encode basically 256 levels of informations. In other words, we can encode up to 256 colors. But colors are very complex. We know that a color usually has a red and green and a blue component, right? For a regular color has a red and a green and a blue component. And when you make combinations out of these 3 colors, out of these 3 components, you'll end up with millions of combinations, much more than 256. Well, this is actually something that was more used in the past, less nowadays, but the image that was encoded here was encoded in a paletted format. It means that besides these pixels, pixel information, it has another area of 256 entries, and for each entry there are 3 values, an R, and G, and a B, right? And all these colors are actually encoded as entries in this one. This is called a palette. And for instance, black is encoded as 0. Red, let's say it's encoded as 1. And blue, it's encoded as 2. And then yellow, it's encoded as 3. And so on and so forth. So in other words, what we have inside the image, we have values from 0 to 255. So in each of the pixels, we have these values. But in order to determine, so this is a pixel. This is a big pixel. Inside each pixel, we have these values. But in order to know in what color to paint this pixel, we make a lookup in this palette. And for instance, let's say this pixel is 10. We look up on the 10 position and we find the RGB colors. All right. So we said that there are 256 positions in the table. So 256 positions times 3 bytes for each position, because encode RGB as 1 byte, equal 768. It's exactly this number. So our file contains an area of pixel information and an area of palette information, and in total it's 480k basically. The only difference is that I represented here the palette at the end. The palette is actually was encoded at the beginning of the file. So our file is encoded as this. Let me draw a bigger file here. I'm just represented linearly, like this, up until here, for a length of 700. So until here, for a length of 768 bytes, we have the palette, which is basically 256 entries times 3. All right, and the rest of the file, we have basically 480,000 bytes, and basically these are bytes. This contains basically the pixel information. So basically each pixel can be a value until from 0 to 155, 1 byte per pixel. And what these are basically, this is because it's 800 by 600, right? That's why we have this number. So 768 and this number. And for each pixel, we have to do a lookup. So each pixel here, we read, for instance, number 10. Well, number 10 at one point here, imagine here, there is number 10 here that contains RGB values. So we'll do a lookup here and we'll find out the RGB for the color 10, right? So these pixels have values from 0 to 255 that represent a color in that palette. 200 to 255 is the maximum. So in other words, our file can contain only 255 color maximum. We know this information. This was used, this kind of trick with a paletted kind of image was used more in the past. On the memory was more expensive, but we also use it as a didactic exercise here. So let's try with this knowledge that we have right now. Let's try to implement a little bit of a display for for our image and see if indeed we decompress it right. So let's implement here function display that takes an image as an argument, and let's walk through all the bytes and plot them on the screen. So we'll assume x goes from 0, x less than 800, x plus plus. Let's loop it with two variables, x and y. Two nested fors, y goes from 0, y less than 600, y plus plus. And let's find the index of that pixel. Let index is basically y times 800 plus x, but we need also to have some sort of let's say let's start equal 256 times 3, and actually the index starts after that start, right? So it start. It's a simple algorithm to locate a value inside the linear array knowing the x and y coordinate. So that should be the index, but it's offsetted by this start because we have the palette in the beginning here. And that byte at that position is basically it's basically image of index. So we have the byte, right? But the byte is like we said, 1 or 3 or 100 and so on. Now we need to find out what color corresponds in the palette for this position. So the position inside the palette, basically, let's say the position, the palette index, pi, pi, the palette index is actually this byte multiplied by 3, right? Because we have for each position, we have 3 bytes. RGB. So if this is, let's say the byte is 0, it will be 0, but if byte is 1, it will be 3, because position 0, 1, and 2 are taken by the byte 0, and then byte 1 starts at position 3. So it's multiplied by 3 here, and now the color, we can say, we can use the p5.js color function, is basically inside this array, which is image, but is actually inside the palette. We read the R from the PI, we read image, we read RG, we read the green, and then we read the blue. All right, so we have a color here, and we can use now the p5.js set function, I think. Set. All right. Yep, we can use the set function to basically, yep, we specify an x, y coordinate, what pixel to put there, and then we call update pixel. We have to call it at the end. That's what P5.js requires. So we are in good shape here. We have the color. So now we can say set X and Y, which we have from over here. We set with the color C. All right. And at the end, we're going to call update pixels. That's how P5.js requires, which actually is based on HTML canvas requirements. So we'll save this one and let's call it. Let's call it here display. Let's call it display image. Let's name it display image. And we'll pass the image as an argument. And let's run it. Surprise, surprise. Save it again. Just not to break on us. And we have an image. So our decompression worked, our display worked, our understanding of the file format worked, and we were able to display it. And we also see this one. So basically, the original file was kind of 480K, and it was compressing about 100K. So it's basically 25%. And we can even see why, because if we can look at this image here, it has wide areas of same color repeating, like this yellow just repeats. So basically probably was the algorithm was able to encode it in a very efficient way. It has kind of simple colors that are repeated, so it's a pretty good candidate for this RLE algorithm. So it is encoded in about 25%. But I actually saved here, let's look for a second. I saved the same image in two other formats. One is BMP format, which BMP is an uncompressed format, and then it's in PNG format. So let's look, it obviously looks the same, but let's look a little bit at the size. The BMP, because it's uncompressed, we can actually see that has the size 481, exactly like our uncompressed structure over here. Look at the inner part here, 481,078 bytes. It's a little bit bigger than our structure, but because BMP has also some other information in the header, which is expected, so it's quite expected. So see, this is an uncompressed one. Let's look at the PNG one here. We're gonna say properties, and we're gonna look at the PNG, and this one, the size on disk, or size actually, is 40K, or 40K. So basically the PNG has even a better compression rate than our simple algorithm, but which is expected. We just spent a few minutes and implemented in 10 lines of code. PNG uses a much better compression algorithm. It actually detects not only a single repeating byte inside the structure, but repeating sequences. If you have byte 1, 2, 3, repeated 1, 2, 3, 1, 2, 3, the compression inside PNG can basically detect that sequence. So it's much more efficient. But other than that, all the images, they are same format, 800 by 600 and 256 colors. Nevertheless, we are not competing here with PNG or any commercial format. This was just a pure didactical exercise to understand the run-length encoding and also play with images. I'm not sure if this is a practical way to encode images in your code, like a series of bytes, although if you want, you can probably do base64 or some form of other, a little bit of encoding on top. All right, let's see if we are able to compress back the same structure, implement like we implemented yesterday, also the compress function. Usually the compressor is a little bit more difficult, but should not be that difficult. All we have to do is basically, if we are looking at the image, we have to scan all the pixels. Actually, not pixels. Well, both compression and compression works on the raw format. It doesn't care what is inside. Could have been Unicode text formatter. But it will work on the bytes. And we'll scan all the bytes and we'll look a little bit ahead. And if in the moment we find a byte, we look a little bit ahead and we check if the next byte following that one is the same as the current one. And if it's the same, we increase the counter, and we also increase the position and look ahead one more byte and one more byte and one more byte, up to 255 bytes, because that repetition can be only 255 bytes. So let's try to implement this compressor function, shall we? Yeah, let's implement it here above the compress. Function compress. There's also some bytes. These times they are the uncompressed bytes, not the compressed ones. But we're gonna try to loop through them in the same way as we did with the compress here, with decompress here. For let I equals 0, I less than bytes.length, and then I plus plus. We loop through all the bytes here. Let's say this is the current byte that we read. It's bytes of I. And now, like we said, we want to compare this byte to check if it's equal or not with bytes of I plus 1, something like this, right? And if it's equal, then we'll increment the counter. So for sure, we're gonna need a counter. Let's say counter here, it's 1. Right now, this byte we suppose is not repeating. So let's implement that comparison, and we'll check not only the next one, but the next one, and next one, and next one, all the bytes until we don't find the repetition. So let's say as long as byte is equal to bytes of I plus 1 to the next byte, what we can do, we increment I here. So in this way, the while will move I, so we'll check first to I plus 1, then because we increment I, we'll move to I plus 2, and so on and so forth. But we also increment the counter, right? Because we found one more byte. But we say as long as these are equal and count is less than 255. Because if we find 500 identical bytes, we still cannot encode them in a single byte saying, okay, it's repeating 500 times, because we need to put the repetition counter on only a single byte. So that's why we say, and as long as count is less than 255, we'll have to split the sequence in basically multiple encoding sequence. So I think we are in good shape here. We just increment this one, right? So at this point, after this while, we should be able to know what is the byte in the sequence and how many times it's repeating, either one time, or if it went through this loop, maybe it's say repeating 5 times, 7 times, and so on. So what we can say is yes, if count is greater than 1, so if we found a repetition, we need to input into the output buffer that special sequence, the 0 marker plus the byte plus the repetition. So let's have an array here, like the output array equal like an empty array. So if we found a repetition, so we'll say ar.push, we push a 0, right? Is the special marker. We push then the actual byte, and then we push the counter, which is this one. So we push a 0, the actual byte, and how many times it's repeating. But remember, we have to push this sequence in one more case. If the count is greater than 1, so if we encounter some repetition, or the second situation when the byte itself is 0. Is that situation, because we use it for a marker, we have to also to encode it. So even if in case we find the repetition or the byte itself is 0, encounter 0, we push this sequence. Otherwise we push just the byte, right? It's a lonely byte there, it's not special marker, it's not something like that. We just push it there. We finish the for, and at the end here we should return AR. All right, so it doesn't have too many lines of code. So let's put also a comment above this one. Compress a series of bytes in a RLE structure, and we're gonna say like this one. Okay, all right, let me save it. Now, how can we test this one? First of all, we can test it on a small array. So let's test it here at the end. let's say let data 2, and we have a series of bytes, maybe byte 2, 3, 3, 3, 3, repeating how many times I put it here, 5 times, byte 4 and 5. And let's say actually this is the original one. Let's say this is image 2, and let's say the compressed one is this one, is compress image 2, and then let's just display them, shall we? We're gonna display first this one, oops, and then we're gonna display this one. Console log is much better than println, but I'm just using this one because I don't have too much screen estate here, space, but you can use console log for these kind of situations. So let's run it, save it, just in case I introduce an error, run it. Okay, let's watch the sequence here. All right, 2 is 2, and then special marker, number 3 is repeated 5 times, which it is, and then 4, and then 5. All right, looks correct. Let's introduce also a weird 0 here. Is that special marker? Let's see that this should be encoded also as 3 bytes. And it is. The last 0 is encoded as 001, which is perfectly correct. Should we put any protections to this function? Let's check it. Like we put for the other one. Maybe here, because the 4 anyway goes up to the length, but here if we found something interesting, we try to go beyond, and maybe we cannot. So you know, it doesn't hurt to put a protection here and say, and if I is less than bytes dot length minus 1, probably the same as before. Hopefully I'm not wrong. Let's run it again. Yeah. All right, so it seems that the compression works fine, but actually we can do a much better job rather than this having this small puny test that we did. Let's remove it or comment it out for a second. And let's do this one. We decompress the image, right? Let's compress it back, which this is a big structure. It's basically it's actually 480K of uncompressed data, and we'll compress it in about 100K of data, and hopefully, you know, there's lots of situation inside, and we should test the algorithm pretty well. And then we decompress it back, and then we display it again. So let's not display here the image. Let's run it. Yeah, it's fine. So we decompress it. Now let's compress it back. So we say compress of image, right? We compress the image again, and now we decompress it again. Image 2, we decompress. Decompress data 2. And when we are displaying, we are actually displaying image 2. Let's save it and run it, and it's working. The image looks identical to me. Now, if we want to be really correct here, or to be really sure, we can implement some sort of array comparison. So make sure that after decompression and after compressions, this array kind of match the 1 with 2, but you know, it's good enough for me. I think we accomplished both tasks, the compression and decompression. All right, so I saved the program. You can find it there on the chat, and you know, feel free to use it in your programs. Although it's a didactical example, probably you won't find too many use cases, maybe for small structures if you want in JavaScript to compress them. But nevertheless, have fun with it. I hope that you learned something new today. And if you are using this one to compress some really nice images, post back in the comments what you compress with them, with the algorithm. As I say, we didn't kind of achieve the compression rate of PNG, which is another lossless compression algorithm, which uses another lossless compression algorithm. But nevertheless, it's 25% of original is pretty good compression for a few lines of code. I hope that you had fun. Thank you very much for watching. Happy coding, and see you next time.